Preparing for an aerospace engineering interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Explain lift and drag, and describe the main factors that influence them. Lift is the aerodynamic force perpendicular to the relative airflow, mainly created by pressure differences and flow turning around the wing. Drag is the resisting force parallel to the airflow. In an interview, I connect them through angle of attack, airfoil shape, Reynolds number, and Mach effects. Increasing angle of attack raises lift until stall, while induced and parasite drag determine the efficiency envelope and drive design choices like aspect ratio, sweep, and high lift devices. While answering, focus on pressure distribution, angle of attack, airfoil geometry, Reynolds number, Mach number, induced drag, parasite drag, and how design choices affect aerodynamic efficiency. Question 2. What is the difference between static stability and dynamic stability in an aircraft? Static stability asks what the aircraft initially does after a disturbance. Does it create a restoring tendency or diverge further? Dynamic stability asks how that motion evolves with time. For example, an aircraft may initially pitch back toward trim, but oscillate with poor damping, which is dynamically weak. I would discuss modes like phugoid, short period, Dutch roll, roll subsidence, and spiral mode, then link stability to center of gravity, tail volume, and control design. Make sure to cover equilibrium, restoring moments, damping behavior over time, longitudinal versus lateral directional stability, and why statically stable aircraft may still have poor dynamic response. Question 3. Compare turbojet, turbofan, turboprop, and rocket propulsion systems. The engineering problem is matching propulsion to mission speed, altitude, and range. Turbojets accelerate a small mass of air to high velocity, so they suit high-speed aircraft, but are less fuel efficient. Turbofans accelerate more air at lower velocity and dominate commercial aviation. Turboprops are efficient at lower speeds because the propeller provides most thrust. Rockets carry oxidizer, so they work outside the atmosphere, but propellant consumption is high. Mission profile drives the selection. In your answer, talk about operating medium, thrust generation, bypass ratio, efficiency by speed regime, altitude capability, propellant requirements, and practical applications for each propulsion type. Question 4. How would you validate CFD results for an aerodynamic design? I never treat CFD as truth by default. I treat it as a model that needs verification and validation. First, I check geometry cleanup, boundary conditions, Y+ values, turbulence model choice, and residual plus force convergence. Then I run mesh refinement studies to see whether lift, drag, and pressure distributions stabilize. Finally, I compare with wind tunnel data, empirical correlations, or flight test results. If trends match but absolute values differ, I investigate modeling assumptions before redesigning hardware. Be sure to mention mesh independence, turbulence modeling, boundary conditions, residual convergence, comparison with wind tunnel or flight data, uncertainty quantification, and checking physics rather than trusting colorful plots. Question 5. Walk me through how you would perform a finite element analysis on an aircraft bracket. I would start by understanding the bracket's function, interface loads, environment, and certification requirements. Then I define material properties, load cases, fastener constraints, and contact assumptions. For meshing, I refine near holes, fillets, and expected stress concentrations while keeping the model efficient. After solving, I review deformation, von Mises stress, bearing stress, and margins of safety. The key is not just getting a result, but proving assumptions with hand calculations, test data, or a validated higher-level model. While answering, cover load cases, constraints, material properties, mesh quality, stress concentrations, factor of safety, margin of safety, validation, and avoiding unrealistic boundary conditions. Question 6. How do fatigue and damage tolerance influence aerospace structural design? Fatigue matters because aircraft structures experience repeated loads from pressurization, gusts, maneuvers, and landings. A part can fail below ultimate strength if cracks initiate and grow over many cycles. I would use SN data for initiation-driven problems and fracture mechanics for crack growth analysis. Damage tolerance assumes flaws exist and sets inspection intervals before cracks become critical. In aerospace, we often combine safe life, fail-safe, and inspectable design because weight is limited, but failure consequences are severe. Make sure to cover cyclic loading, crack initiation, crack growth, SN curves, fracture mechanics, inspection intervals, fail-safe design, safe life design, and why aerospace structures need conservative margins. Question 7. What causes an aircraft wing to stall, and how can designers delay or manage stall? A stall occurs when the wing exceeds its critical angle of attack, and airflow separates enough that lift drops sharply. It is not caused directly by low speed. Low speed just often requires a higher angle of attack. Designers manage stall with airfoil selection, washout, slats, flaps, vortex generators, and careful wing planform design. A good design makes the root stall before the tip, so ailerons remain effective. Operationally, pilots rely on stall warnings and angle of attack awareness. In your answer, talk about critical angle of attack, flow separation, stall progression, airfoil shape, twist, leading edge devices, vortex generators, warning systems, and controllability near stall. Question 8. Explain the basic orbital mechanics behind placing a satellite into low Earth orbit. To reach low Earth orbit, the vehicle must gain enough horizontal velocity that it continuously falls around Earth rather than back to the surface. For LEO, that is roughly 7.8 kilometers per second, excluding gravity and drag losses. The launch vehicle climbs through the dense atmosphere, pitches over, sheds stages, and performs a circularization burn near the target altitude. Inclination depends strongly on launch site and mission needs. The main idea is not simply going high, it is going sideways fast enough. Be sure to mention orbital velocity, gravity as centripetal acceleration, launch energy, inclination, staging, circularization burns, atmospheric drag, and why reaching orbit is about horizontal speed. Question 9. What are the advantages and challenges of using composite materials in aircraft structures? Composites are attractive because they offer high strength-to-weight ratio, corrosion resistance, and the ability to tailor stiffness by fiber orientation. That makes them excellent for wings, fuselage panels, fairings, and control surfaces. The challenge is that they are anisotropic, process-sensitive, and can hide impact damage or delamination. Design must consider layup sequence, load paths, moisture, temperature, and inspectability. Compared with metals, composites can save weight, but they require disciplined manufacturing control and specialized non-destructive inspection. While answering, focus on strength-to-weight ratio, anisotropy, layup design, delamination, impact damage, manufacturing variability, inspection methods, repairability, and comparison with aluminum alloys. Question 10. How would you approach thermal management for a spacecraft or high-speed aircraft component? I start by mapping heat sources, heat paths, and allowable temperatures. In spacecraft, radiation dominates because there is no atmospheric convection, so surface coatings, radiators, multi-layer insulation, and heaters become critical. In high-speed flight, aerodynamic heating and conduction into structure may dominate. I would build thermal cases for hot, cold, transient, and worst-case operating conditions. Then evaluate material limits and thermal stresses. Thermal design is always coupled with mass, power, packaging, and structural reliability. Make sure to cover conduction, convection, radiation, heat sources, insulation, heat sinks, active cooling, material limits, thermal cycling, and coupling thermal analysis with structural performance. Question 11. Describe how a flight control system maintains aircraft stability and command response. A flight control system turns pilot or autopilot commands into controlled actuator movements while keeping the aircraft stable. Sensors measure attitude, rate, acceleration, air data, and sometimes position. The controller compares desired and measured states, then commands elevators, ailerons, rudder, or thrust vectoring. Simple systems may use PID logic, while advanced aircraft use gain scheduling or state space control. The design must preserve stability margins, handle sensor failures, and include redundancy, because flight controls are safety critical. In your answer, talk about sensors, actuators, feedback loops, control laws, PID or state space control, stability margins, redundancy, failure modes, and pilot command handling. Question 12. How do requirements in systems engineering shape an aerospace project? Systems engineering keeps a complex aerospace product from becoming a collection of disconnected good ideas. I would begin with mission objectives, then decompose them into measurable requirements for performance, mass, safety, cost, reliability, and interfaces. Each requirement needs verification through analysis, inspection, test, or demonstration. Traceability matters because a change in payload, range, or thermal environment can affect multiple subsystems. Good aerospace engineering is technical, but it is also disciplined communication, configuration control, and risk management. Be sure to mention requirement decomposition, traceability, verification and validation, interfaces, trade studies, configuration control, risk management, and communication across aerodynamics, structures, propulsion, avionics, and manufacturing teams. Question 13. Tell me how you would perform a trade study between two aircraft design options. I would first define the decision clearly, such as choosing between two wing planforms or materials. Then I establish evaluation criteria: weight, drag, cost, manufacturability, maintainability, safety margin, schedule risk, and mission performance. I assign weights with stakeholder input, score each option using data where possible, and run sensitivity checks so the result is not driven by one weak assumption. A good trade study does not just pick a winner. It explains uncertainty and what testing could change the decision. While answering, focus on defining criteria, weighting metrics, assumptions, constraints, sensitivity analysis, risk, cost, manufacturability, performance, and documenting why one option is preferred. Question 14. How would you plan and evaluate a flight test for a new aerospace system? I would begin with clear test objectives tied to requirements, not just a desire to collect data. Next, I define instrumentation, telemetry, calibration, safety limits, abort criteria, and the planned envelope expansion sequence. Early tests should be conservative and build confidence before moving to higher risk points. After the flight, I compare measured data with analysis and simulation predictions, checking both performance and anomalies. The best flight test programs are disciplined, incremental, and honest about uncertainty. Make sure to cover test objectives, safety planning, instrumentation, envelope expansion, data quality, telemetry, go-no-go criteria, risk mitigation, and comparing results against predictions. Question 15. If an aerospace component failed during testing, how would you investigate the root cause? My first step is to preserve the evidence and avoid jumping to conclusions. I would document the failure, collect test data, review loads, boundary conditions, instrumentation, environmental conditions, and any deviations from procedure. Then I examine the hardware through visual inspection, dimensional checks, material testing, and fracture analysis if needed. I compare findings with design assumptions, manufacturing records, and FAA predictions. The final output should identify root cause, corrective action, and verification steps to prevent recurrence. In your answer, talk about preserving evidence, reviewing test conditions, material inspection, fracture analysis, design assumptions, manufacturing records, load paths, corrective actions, and preventing recurrence. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.